Hello student to the course for Foundation of Classical Electrodynamics. So, today we have module 2 and under module 2 today we will going to study the dielectric and that we started in the last class. We will going to continue more topic on dielectric. So, we have class number 43 today, and we will continue our discussion on dielectric. So, let us find. So, if I have a chunk like this which is a dielectric material, and if I apply some external electric field E like this. So, under this external electric field I place the dielectric, and as a result what happened that tiny dipoles will going to form. If I try to present this pictorially, so there will be charge separation like this, and we will have a dielectric system here. Well, now we know that this quantity should have a property called polarization, which is the dipole moment per unit volume. So, that polarization P is proportional to E. So, I can write this proportionality constant at alpha, and the expression, the relationship with the electric field and polarization I can write in this way. Now, here what I mention is, so P is proportional to the strength of the applied electric field, that is, and not only that, it is the same. I mean, if the two vectors are, if I write in like P as Px x unit vector say plus Py y unit vector plus Pz z unit vector. So, that is in vector form, and then I can have alpha, then Ex x unit vector plus Py y unit vector plus Ez z unit vector. Okay. So, that eventually means that Px is equal to alpha of Ex and Py is equal to alpha of Ey and Pz is equal to alpha of Ez, right. Component wise they are same. That means, the x component of the polarization vector depends on the x component of the applied electric field, y component of the polarization vector will depends on the y component of the electric field, and z component will depend on the z component of the polarization will going to depend on the z component of the electric field, and all the cases this is alpha. So, if I so here alpha is the polarizability of the system. polarizability. Now, for this case what happened, that if I have a coordinate system like this and if I apply the electric field, say having 45 angle, and then the two components of the electric field, say I can write like this is my Ex, this is along E unit vector and this is along Y unit vector, and this is my Ey, and whatever the Pi plot here is in the same direction, and I should also have Px here and Py here. This is my P vector and this is my E vector. So, this is the most simplest case, but here I mean if alpha depends on the direction of the applied electric field. So, now alpha depends on the direction of the applied electric field that means the okay. So, let me draw another case like this is my coordinate system x and y. Let us consider only 2 dimension, and this is the direction along which my electric field is applied, but my polarization now is no longer in the same direction of the electric field here, but the x component of the polarization is still depends on the x component of the the electric field. So, this is my electric field. So, electric field should have Ex along x direction, this is Ex and this is Ey, and the polarization Px is still depends on Ex and Py still depends on Ey, but like before the ratio is not same. That means now Px depends on still depends on Ex, say, but I should write here this alpha as say Xx Ex, and for Py it is alpha say Yy Ey, when alpha Xx is not equal to alpha Yy. This is one condition we can think of. So, that means the alpha previously it was a scalar quantity, but now we find that it should have different components, and that is why it no longer become a scalar quantity, rather I should have a tensorial form of alpha, because if now here what happened, the x component of P depends on the x component of E. Still we have these things, but more general situation can be considered, and that is the x component of the more general case is. So, I can pictorially I can show that the most general case. And the most general case is when E suppose I have this coordinate system and my E is along this direction, some direction, P is not parallel to E. So, it should have some other direction. Not only that, so this is my E x, suppose I divide, this is my say E x and this is my E y. I can separate coordinate the component in x I y direction, but whatever the P I am having, its x component does not depends on only E x, it can also depends on E y. So, so maybe I can draw in this way. So, P 1 I can say its another component here is P 1, maybe in different color. I can divide it into two components like P 1 and say P 2. See, this is my full P component, and I can have these as a combination of P 1 and P 2, and here you can see that it is not parallel, but also the I mean if I divide this stuff, then the x overall x component of P, overall x component of P now not only depends on the x component of E, but the y component as well. And now I can have these here the constant E x x and E x y, because here the x component of P does not depend on the x component of E, it also depends on the y component of E. In a similar way, the y component of the P can also depends on the x component of the E plus the y component in 2 dimension y component of the E, and in that case I should write here as like y x and alpha y y to distinguish these things. So, in general for 3 dimension, this is for 2D, in general for 3 dimensional case. So, P x component can depends on E x, E y and E z, and now I can write it like alpha x x plus alpha x y plus alpha x z, and my E component will be like E x, E y and E z. In a similar way, I can write P y and P z. Explicitly if I write, then I should write here alpha y x plus alpha y y plus alpha y z, alpha z x plus alpha z y plus alpha z z, and the components are Ex, here I should write Ex, here I should write Ey, Ez, Ez. So, my electric field is E and my polarization is Pz, P, but the x component of these things depends on the xyz component of the E and so on. So, I can write this entire thing in matrix form, and if I do, I simply have this P x, P y, P z is equal to alpha x x, alpha say x y and alpha x z, alpha y y, alpha y x, sorry, alpha y x, alpha y y, alpha y z, alpha z x, alpha z y, alpha z z, bracket close, and the electric field which is the component wise E x, E y and E z. This is, so alpha is simply the polarization tensor. This quantity is called the polarizability tensor. And I can write it in this convenient form, it is called component form. P I is simply alpha I j E j. In Einstein notation, the summation is over repeated index. So, I simply have this. So, this is the one important expression for this polarizability, where we can show that the polarizability is in fact a tensorial quantity, and there are different system for which if you apply the electric field, the polarization is no longer along the applied electric field, there will be a different direction, and not only that, its x component, y component and z component no longer depend on the x component, y component and z component of the electric field alone. The x component of the polarizability can be depend on the x, y, z component of the applied electric field, and in that case we are having these generalized form. So, from here you can simply find that if it's only P x is only depends on E y and P y is only depend on P x is only depend on E x, P y is only depend on E y and P z is only depend on E z, and the dependency is same, then we should have a diagonal matrix where alpha x x, alpha y y and alpha z z both are, all three are same, and we just simply write alpha, then it simply becomes a scalar equation which we wrote in the beginning, this equation. Okay. But in general, alpha is not a scalar quantity, it is a tensor quantity, and how it become tensor we try to explain briefly here. Okay. Now, we discuss about a important thing, and that is the field associated with a polarized object. So, next topic is the field of a polarized object. So, what does it means? So, suppose a polarized object is there, and there should be a charge separation in between this polarized object, and this polarized object should give us some kind of polarization, and that means some kind of dipoles are there, and that dipoles give rise to some dipole moment. So, because of that we should have a field, right. For a dipole we calculate a field, and here something like happening, something a similar kind of things will happen. So, we can find a corresponding field or corresponding potential due to the polarized object. So, let us try to find out how to get it. So, suppose I have a coordinate system here like this, and a polarized object is sitting here, and it is characterized by a dipole moment, and this is the dipole. Normally this is the way we define a dipole, and polarization is eventually dipole moment per unit volume. So, now what should be the field due to this we can calculate, and the location wise I need to. So, the location here, this coordinate is my r1, say r prime. So, from here to here, this is the field where we try to find out the field, curly r, our standard notation, and from origin to this value, this is my r. Okay, this is the system. So, polarization P, as I mentioned, polarization P is dipole moment per unit volume. So, P is big P dV. Dipole moment for a volume element is dV prime. So, if I want to find out the dipole moment per unit volume, then I need to divide that. So, dipole moment for a, so this is big P is dipole moment, P, small p is dipole moment for a volume element dV prime. Small volume element, this is the dipole moment I have. So, now for a potential for a single dipole, that we know, right. So, the potential for a single dipole is simply phi r. We calculated this is equal to 1 by 4 pi epsilon 0, and dipole moment dot r unit vector divided by r square, because the potential for dipole goes like 1 by r square. So, this is the form. Now, for total potential for the volume, so the total potential for the volume for the entire volume. That should be the integration. I need to put an integration because so phi of r for total should be equal to 1 by 4 pi epsilon naught and integration p r prime, okay, then dot r unit vector divided by r square, and then I integrate over the entire volume. So, I have dv prime. So, for dv I have, for single dipole I have this, and for the entire volume I need to integrate it over this. So, r vector r is simply r minus, so it is r minus r prime, and r square simply mod of r minus r prime square of that. So, r unit vector r divided by r square, that term which is there inside the integral, I can write it as r minus r prime divided by r minus r prime cube of that. Now, we can have this. So, this is a well known thing that if I want to make a gradient of this vector, this quantity 1 by r minus r prime, in many places we have to use this, then the result is plus r minus r prime divided by r minus r prime cube, that quantity. So, the positive sign because I am making the derivative with respect to prime, and we have a negative sign already here. So, eventually I can write unit vector r divided by r square is equivalent to the quantity 1 divided by r. Okay. So, now I am going to make use here in this equation, and I can write it as my phi r, the potential is 1 by 4 pi epsilon naught, and then integration p r prime, and then dot r r unit vector divided by r square. I just replace this quantity prime and then 1 divided by r, which we get here, okay, and then dv prime. Now, I am going to use another vector identity, that prime dot p divided by r, the vector identity is saying that it is p dot prime 1 by r plus 1 by r and then prime dot p, and that we will going to use here, that my phi r will be 1 by 4 pi epsilon naught, and if I integrate and make it 2 part, then this quantity whatever I have I am going to replace here. So, this quantity I am having here. So, this I replace by this minus this, and if I do, I should have say divergence. Okay, my pen is not working properly. Divergence of P by R dV prime and minus 1 by 4 pi epsilon naught, and then integration 1 by R, and again I have prime and then P, and that should be in R prime and dV prime. Okay, so now I can use this as my this integral I can replace to a closed surface integral, because this is divergence of this quantity over volume. So, I can make it a surface integral like simply P divided by R, and that is over R prime and dV prime. And the next integral, I here the operator is over over this. Okay, so next integral I simply write 1 divided by 4 pi epsilon naught, and then integral 1 by R, and I absorb this negative sign to write minus of this dot P R prime bracket close dV prime. Okay, so 2 term I find, and these 2 term I can now write these 2 term in this way, because one is surface integral and another is volume integral. So, I can write it 1 by 4 pi epsilon 0, then the closed surface integral, and then I write the bound sigma b like a bound charge density, then 1 divided by R, and then dV prime, that is my d here. Okay, I make a mistake here, because I make a surface integral. So, this should not be V, and this should be ds prime, and here also it should be ds prime, ds prime. Okay, plus 1 by 4 pi epsilon naught, and next term I can write is this, I write rho b volume charge, bound volume charge density, the term called, and then dV prime. Okay, so how you define that? So, I can define in this way. So, sigma b is equal to p vector dot n. This is called the bound surface charge density, and rho b, which is minus of divergence of P, that quantity is called bound volume charge density. from the expression of the potential you can see that this is my phi, and if I just look carefully that this is a function of r. So, it is contributing with two terms. First, here the term where we have a surface charge density and we say bound because it is a polarized object, and because it is a polarized object it should have some bound charge. And another, here we have another contribution where we have a bound volume charge density. So, as if the potential is a contribution of a charge which is bound and this charge is entirely over the surface, and another contribution of the another set of charges which is again a bound charge, but this is a volume bound volume charge density. That is why it is over the integral over volume and integral here the integral over surface. Now, let us try to understand the physical interpretation quickly, the physical interpretation of this bound charge densities, whether it is surface or. So, the next thing is the physical interpretation of bound charge. So, what is the physical interpretation for the bound charge? For example, you have a long string of dipoles. So, long string of dipoles means I have here like this. So, and then this is, so if I join this is a chain of dipole where we have plus charge here, minus charge here, plus charge here, minus charge here, plus charge here, minus charge here. So, these are minus charge, minus charge, minus charge. That is simply equivalent to, because these plus charge and minus charge in between they can cancel it out as if they are cancelling each other, and eventually we can have an equivalent system where we have only the leftover charges in the boundaries, and that is minus plus here and say minus here. So, I have only one dipole. So, there is a charge, even though there is a charge, the entire charge is nullified, but in the surface I can have a charge that is not being nullified. So, I should have effective charge in it. These charges are bound charges, that is why I call the surface bound charge. So, we can understand in terms of this tube of dielectric. Let us consider a tube of dielectric and as if I have a cylindrical shaped tube made of dielectric, where this is the area A and this is the length D, right, and it can be equivalent because the way we mentioned that only the leftover charge is here. So, this is the leftover charge sitting at the boundaries. So, I have a leftover charge that is sitting over this boundary, and eventually I can consider these as a dipole having the charge here, say minus q and plus q sitting here and here. So, the dipole moment, if I want to calculate this, the dipole moment of the, because I make it as equivalent dipole because of this leftover charge whatever we get. So, dipole moment of the chunk is simply P equal to P V, V is the volume and this is dipole moment per unit volume. So, that is equivalent to P and the volume is A multiplied by D, because A is area and D. Now, the interim charges, so in terms of charge q, what should I write? The dipole moment P is simply q multiplied by D. So, here this dipole moment P, which I have an expression like P A D, is equal to q multiplied by D, that is the dipole moment. And now from here we can see that P multiplied by A seems to be q and P is q divided by A, and that is polarization, right. Q divided by A is nothing but the charge divided by surface. So, charge divided by area. So, this is the bound surface. I can have the expression of bound surface charge density. Well, if in general, if the surface is, there is a say surface is like this and the n is along this direction, that is the direction of the surface, and my polarization P is along this. So, this sigma b is simply q divided by the end, whatever the area we are having, and in order to take this, if this angle is theta, so I need to take the component, cos component. So, it should be P of cos theta, which is equivalent to P dot n unit vector. So, eventually what I find that my surface volume charge density is nothing but the polarization along the surface. So, P dot n, this is the relationship between the polarization and the bound surface bound charge density. So, that is the relation we qualitatively understand. Then another quantity we need to understand qualitatively, and that is the bound volume charge density. So, the bound volume charge density bound volume charge density, suppose I have a, so if say the polarization is non-uniform, suppose we have a polarization of the system, but this is non-uniform. If the polarization is non-uniform, one can get the accumulation of bound charge of bound charge accumulation of the bound charge within the material within the material as well as surface. So, what is the meaning of that? Suppose I have a system here dielectric, but the polarization is not uniform throughout. So, suppose we have a bulk of negative charge sitting here and some positive charge is here over the surface. So, this is the way the charge is distributed, but this is not uniformly it is not distributed uniformly. Now, the divergence P results in a pile of negative charges, and net bound charge, whatever the net bound charge we are having, is simply I can write it as the bound charge density over dV, right. This is because whatever the net charge, and this is equal to the in a given volume, this volume, and it is equal and opposite to the amount of the charge that is pushed out through the surface, whatever it is. So, it is equal and opposite to that thing that one can push out like this. So, we have a feeling of divergence here, and that feeling I can write it as this is equal to minus of, because it is pushed outward. So, I can have a P dot ds, because this is over the surface and that is why it is closed. So, I can have this quantity, and that is minus of, according to the integral law, we have a closed surface integral. So, that should be equal to the volume integral, Gauss's law, and from that we can have that rho b is equivalent to minus of divergence of P. So, what I get, let me write properly, otherwise. So, as if, so what we are getting here is this, the say diverging P, the divergence of the P results in a say pile of negative charge as per the figure, and the density of this quantity is simply D. The net bound charge, the net bound charge, which is this quantity, integral of the volume charge density, where it is bound. So, that is why this written as rho b in a given volume is equal and opposite to the amount that has that has been pushed out through the surface. So, I pictorially show that suppose I have a negative charge. So, this divergence is simply equivalent to whatever the the volume charge density we are having. So, eventually we have a we get this very important equation that if there is a variation of the polarization, so that variation of the polarization can be quantified with a divergence, and the negative of that divergence value is eventually the density of the bound charge that is produced. So, whenever we have a non-uniform polarization, then only the concept of bound charge is there. If there is no non-uniformity of the polarization P, then what happened if you take the divergence of that quantity? So, that will be simply 0 and you will not going to get any kind of bound charge out of that, bound volume charge density out of that. So, today I do not have much time. So, I like to conclude my class here. So, in the next class we will continue a few more things related to the dielectric properties of the material, and we see some boundary conditions also, that how the boundary condition of the electric field will going to modify, because in that case we should have something called displacement vector. So, how displacement vector come and what should be the boundary condition we will discuss. So, with that note I would like to conclude here. Thank you very much and see you in the next class.